Thanks to the organizers for putting up this nice workshop. So this is a set of works done with Sean Hartnell from Cambridge, Aditya Hebbar, who is a postdoc at ICTP, and Ruby Kondakar, who is a PhD student at Oxford. This picture, it's an essence of what I'm going to be talking about. So this is basically, I believe, an illustration from the book, The Adventures of Baron Munchausen, where the story is like, the illustration is from the story where he lifts himself out of the swamp by pulling on his own hair. I will propose a less violent way to do physics. We will be doing so by pulling ourselves up using our bootstrap. Okay. Yes. So this will be the outline of the talk. I am a high energy theorist, so I'll need to provide some motivation as to like why I'm doing what I'm doing. Then there will be the setup. We will then derive the bounds, and there will be some applications, and I'll conclude that. So, what does bootstrapping mean? Okay, so it means that I want to solve a system or a problem using consistency conditions as much as possible. Okay, so the point of view that I will take is that the world around us is modeled by effective field theories, which means that we don't necessarily care about the details of from which microscopic theory it has emerged. We usually write down a Lagrangian in a derivative expansion with the higher order terms, like the more irrelevant terms, suppressed by some cutoff scale. Okay? This cutoff scale will be is the scale up to which our effective field theory would be kind of valid, right? And the bootstrapper's question is the following. Okay. Now I mean, the microscopic details of where it has come from is not completely lost. It's within this coefficients in terms of these high derivative terms. These are called.
Turn off your microphone.
Oops. I think I have turned it off. I'm not.
Okay.
Yeah. I'm not on. Yeah. So now these Wilson coefficients encode what is the microscopic theory. Okay, this is usual effective field theory as Wilson had envisioned it. Okay, now the bootstrapper's question is the following: that can we say anything about these Wilson coefficients, which are these lambda, lambda prime, and so on and so forth, without any assumptions about the microscopic theory, any detailed assumptions about the microscopic theory? And the answer turns out to be yes, provided you just make some minimal assumptions. For example, that the microscopic theory is Lorentz invariant, it's causal, it's unitary, conditions, very general conditions like that. And at least in high energy theory, like this has very far-reaching consequences. For example, it can be used to ask the following questions, such as what effective field theories of gravity have a UV completion, which is a fundamental question that we are interested in. And more recently, it has also led to understanding what sort of gapped or gapless phases of matter can arise from deforming conformal field theories. Okay, for example, by finite chemical potential, you put it at finite temperature, or even like put it at high magnetic fields. Okay, so these are the sort of questions that I'm interested in, and it's a well known that these EFT parameters, this lambda, lambda prime that I just showed you in the previous slide, they just cannot take any arbitrary value. Okay, not every effective field theory can be UV completed by a nice UV completion. Okay? And this is basically manifest through the observables in quantum field theory, such as scattering amplitudes and Green's functions, which must obey certain analyticity and boundedness properties because of Lorentz invariance, causality, and unitarity. So if you vary around these effective field theory parameters too much, you will find that these conditions get violated. And so therefore, we are led to bound on these effective field theory parameters. Okay? And just to give you an idea, because we will more or less follow this kind of logic, I'll just give you a brief overview of how this works in relativistic field theories. Okay, the central object that we want to look at is the scattering amplitude. Okay, so you prepare states in the far past, you let them interact with each other, and you measure the probabilities of outcome at distant future. Okay, and you assume that the theory is the microscopic theory is Lorentz invariant, unitary, and microcausal. Okay, and this tells you certain properties, as I was saying, certain properties of this this probability, which measures how they interact, must be certain properties of this object, this scattering amplitude. Okay, for example, microcausality, which basically means that operators commute at space-like separation. This tells you that this object M, which encodes this scattering amplitude, it must be analytic as a function of this Mandelstam invariance. Okay, this scattering amplitude, if we are just looking at 2 scattering amplitude, they are parameterized by just 2 parameters, this S and T. These are the Lorentz invariant combinations that you can build out of the momenta. Okay, and there is certain analyticity properties of this scattering amplitude. Okay, the second ingredient is unitarity, which is basically a statement that sum of probabilities should be 1. Okay, and it can be used to give some bounds on discontinuities of this M, which essentially means the imaginary part of this M. And just like you do in usual condensed matter physics, like you write down some sort of a relativistic analog of Kramer's-Kronig relation, which take this form. These are essentially some sort of dispersion relations. Okay, and it basically relates the amplitude to over some spectral decomposition at high energies. Okay, S basically, like, you can think of it as basically center of mass energy. Okay, and that's where the effective field theory comes in, because so far there was no, this is true for any theory, microscopic or effective field theory. Now that's where this is now where the effective field theory comes in, which is that at low enough energies, this left-hand side of this sum rule, it can be completely evaluated in the effective field theory. Okay, you have your effective Lagrangian, and order by order in derivatives, you can actually compute this object. So what this tells you is that it relates the EFT parameters with the properties of the UV completion. Okay, and this has led to many kind of constraints on low energy parameters just by demanding these simple conditions on your UV completion. For example, one of the seminal papers in this regard by Nima and collaborators, they showed that, for example, that if your low energy effective field theory is described by massless bosons with a shift symmetry, the leading irrelevant operator must have a sign definite. It must be sign definite. Okay, everything comes together to show you that this must be true. Otherwise, this cannot be embedded in a UV complete theory. Okay.
So can you say again what H and H tilde are?
These are some kernels. I'm not going to be it's not, it's just schematic. It's some kernel that you use to write down the dispersion relations, and that's it. Like at the moment, this will not play any sort of role in what I'm going to talk about next. Yeah. So any questions so far? Like, okay. So so the question then that I want to ask is the following: that okay, I mean, these conditions, this entire program assumes that you have an explicitly Lorentz invariant UV completion. Okay. Now, of course, like for day-to-day condensed matter system, you don't really need Lorentz invariance. Okay. So the question is like, can you? I mean, how do you set up a bootstrap problem for that? So, for example, me and my collaborators, we started by asking that, can you, instead of assuming a Lorentz invariant microscopic theory, can you assume what are the consequences if you assume, for example, it's UV completed by a lattice system? Okay? So that is the question that I want to answer, and hopefully I can convince you that this sort of approach has some sort of teeth. Okay. So so let me describe what my setup is. Okay. My setup is the following: that I will consider a local bounded Hamiltonian on a d-dimensional square lattice with lattice spacing A. Schematically, this will be of this form, where alpha is some sort of lattice position, and apart from this, I won't demand anything or assume anything about the details of the Hamiltonian HA, except these boundedness and locality. Okay, so what does boundedness mean? The condition of boundedness is basically like, if you say an operator is bounded, what you do is you take the expectation value of that operator within all the possible Fock states, and you look at the maximum eigenvalue that you can obtain in such a way, and that must be bounded. Okay, that's the statement. Okay. The second criteria which I require is that of locality, which means that like it will act at most on our nearest neighbor sites. Okay, these are two mutually exclusive conditions that I'm demanding on my Hamiltonian, and it will be sufficient to satisfy both of these conditions if I consider, for example, a finite dimensional Hilbert space at each lattice site, which roughly means that I'll be considering mostly fermionic Hamiltonians, and a local its nearest neighbor interaction. Okay. Yeah.
So I mean, you just said it, but so you will explicitly be ignoring anything to do with phonons, since you have infinite.
Yes.
I see. But in trying to understand solids, that's probably important.
Yes, absolutely. I'm not claiming that I'm solving, I'm bootstrapping everything there is in condensed matter, but I'm just, this is somewhat of an initial step towards a more of a larger program, if you wish. Indeed.
So for clarity, you're saying this lattice you're using to represent a real physical lattice in the material, rather than some discretization, some UV regulation of.
No. Yeah. I mean, take some Hubbard model and like.
So the finite dimensional Hilbert space, that's an assumption?
Yes.
Or, okay, so it's not just these two boundedness.
So this is sufficient to ensure these two conditions, that you have a finite dimensional Hilbert space and a nearest neighbor interaction. Right. Okay. That's it. It's not necessary, but it's just sufficient. Okay. So since we are in a system where there is no Lorentz invariance, we can't use S matrices. we will just throw it out. And what our observable is going to be are correlation functions, retarded correlation functions of lattice operators. Okay. Now, in principle, in order for this bootstrap-like program to be, useful, you would want to use correlation functions of conserved operators, because conserved operators are the only ones which you can unambiguously identify both in the UV and the IR. Okay, but just for illustration purposes, like let me start with, for example, the fermionic Green's function. For example, just to illustrate these kind of bounds. These bounds are, okay, I'll be considering finite temperature, retarded Green's function. Okay, now the first condition that I want to impose is that of analyticity. Okay, so let us recall how it works in relativistic systems. So in relativistic systems, the analyticity comes from microcausality, which is that, oh, the operators must commute at space-like separation. Okay? And how does it lead to analyticity? You look at the Fourier transform of the Green's function. Okay? And in order to look at this, probe this analyticity, you look at the Green's function in imaginary frequency and momenta. Okay, the statement is that this Fourier transform must exist even for imaginary frequencies and imaginary momenta. Okay, as you can see, then because of this prefactor, it can for imaginary frequencies and momenta, it can become real, and so you would have some sort of tension where this Fourier transform may not be well defined. Okay, and if you follow your nose, you will find that in order for this to be valid, you have this kind of this Green's function is analytic within this domain, in this light cone-like object in imaginary frequency and imaginary momenta. Okay, and now for non-relativistic systems, of course, there is no light cone. How do we expect analyticity in this respect? Okay, but now since I'm looking at local systems, there is still a notion of causality, okay, which is this Lieb-Robinson causality, which basically constrains how an operator spreads in time. Okay, and and for example, if you look at this 1D system, which I took from one of Andy's reviews, it tells you very nicely that, for example, if you start with the ground state, you have this light cone-like structure emerging as you evolve in time. Okay, and so there is still a notion of how fast information can travel. Okay,
but it's embedded in the definition of retarded correlation functions. There's already some analyticity requirements, right? That they have to be analytic. The upper half plane and all this stuff.
For real momenta.
Right. Okay. Good. So here you're.
Yes, I'm also. Yes. Yeah. Okay. Yeah.
Thank you.
Yeah. Because for real momenta, you see, it's just this term which will damp it, and so automatically relativistic system, non-relativistic system don't really are not much different.
Right. Okay. Thank you.
Yeah. Okay, so let me give you a flavor of this Lieb-Robinson bound. So what we want to do, remember what we want to do, we want to understand where our Fourier transform converges, okay? And the central ingredient there is this Green's function, which is this. And essentially what we want to do is, and to estimate how big this guy can be as a function of t and x, such that we have, so that we can determine where it is converging and where it is not, where the Fourier transform is converging and where it's not. Okay. So basically, this turns out to be estimating this norm of the commutator okay, norm of the commutator. And you can convince yourself that if you look at this psi dagger t and you write it as e to the power iht, psi dagger e to the power minus iht, and you expand the commutator, what you are estimating is this basically like, how large can this commutator, this k commutator be? Okay, because like at each step you have like h commutator psi coming out. You do the BCH kind of decomposition, and like you have this. Okay, and just to give you a flavor, for example, like at time t equals 0, if you are localized on this, it's this red dot. Then I'm just assuming just nearest neighbor, but you can do it for r nearest neighbor. So in the second step, in the second time evolution, you will have access to these sites, these surrounding sites, and in a d-dimensional lattice, you have this commutator can be estimated by this. This will have this many terms, okay, and as you go on, you similarly like have higher and higher number of terms, the commutator. Okay, so it's basically this. Okay, and there is a way to formalize this. This was done by Hastings in quite some time back, and what you get out of this is that this norm of this commutator is basically upper bounded in this manner. Okay, so for in terms of lattice length, for when the x, the distance is less than EHT, where H is defined in this manner in terms of the norm of each of the Hamiltonian H alpha, there is a light cone. But unlike relativistic counterpart, unlike relativistic systems, the support does not go to 0 outside of the light cone. It has some sort of an exponential decay outside of the light cone, which you would kind of expect for non-relativistic systems. Okay, so there is a light cone. Light cone defined by this trajectory in momenta, position and time, and the velocity, Lieb-Robinson velocity, for this case is given by this. Okay, any questions so far?
Can you remind us the meaning of the symbols? A, I guess, is the lattice spacing.
Yes, lattice spacing. H is defined by this.
Related to the norm of the Hamiltonian.
Yeah, norm of each individual term of the Hamiltonian. Okay, so it's finite. It's not something like blowing out of proportion. Okay, so that's the Lieb-Robinson bound. And now what we want to do is basically perform the same exercise as one does for relativistic physics, which is that like I want to understand how the Fourier transform converges in complex frequency and momentum. Okay, so what we do is that we choose this kind of this imaginary momenta and frequency, and then we estimate what are the conditions for omega and q such that this is exponentially damped. The integrand is exponentially damped. Okay, there are two parts. The first part is kind of the leakage outside the light cone. You have to bound that part. And then the second part is kind of very similar to relativistic theory. And if you work it out, you will find that you land up in this analytic region. Okay, there is an analyticity light cone for this omega 2 less than E of H. Let me present you a more pictorial version of this. That if you plot the imaginary omega and imaginary imaginary momenta and imaginary frequency, it turns out to have this kind of a light cone-like structure up to a certain point, and after that, this has this kind of exponential region of analyticity. Okay, so there exists an analyticity region for locally bounded Hamiltonians in complex frequency and momenta plane. Okay. Any questions so far?
Are you going to connect this to something more physical?
Yes. That will be the applications. Like I will. Yeah. Okay. So the second ingredient that we want is unitarity, okay, which for again recapping our relativistic physics idea is that it basically tells you that if you, for example, remember that our central objects in relativistic physics were scattering amplitudes, and you can decompose them in terms of like something, these are called partial waves. Basically, you write them in some angular momentum basis, and you get some bounds on these coefficients, which encode the details of the interaction of the theory. Okay? And one question one can ask is that what is the analog of this for Green's functions? Okay? And it turns out that it basically, the analog of this is bounds on the imaginary part of the Green's function, but now for real omega and real k. Okay, how do we get this bound? So you have this retarded Green's function. You insert some complete set of states, and you get this kind of spectral decomposition. This is very general. This is standard stuff. And notice that all of them are positive, as you would expect. So now the question is like, this has all sort of delta functions. How do you, make sense of any sort of upper bound from this? Delta functions are like not nice, so to speak. So the way you would do it is that then you would basically smear over the real frequency and real momenta of this. Okay. What happens when you do this? So on the right hand side, you have a sum of delta functions. So when you integrate over the frequency and momenta, you pick out some of the delta functions, which will be there. Okay, but then you realize that okay, on the right hand side, it's basically like it's a sum over positive terms. What you then do is that you throw back in whatever term was excluded by the delta functions, so that now it's an unrestricted sum over m and n. Okay. You are allowed to do that because essentially what you're adding back are positive terms. Okay, and once you do that, you will find that this is basically like it's upper bounded by the thermal 1-point function of the O0 square operator. Okay. This is one of the bounds that you can get in this map. Okay.
This almost looks like a fluctuation dissipation, or
yeah, it's close, but it's not the same. It will become clear in the second slide as well. Okay. You can do another trick to get this. So the entire this entire game is basically like how clever can you be in like estimating what sort of what can be the upper bound on these kind of Green's functions. Okay, this that is the game here. If you can probably make these bounds better as well. Okay, and so one of the other tricks that you can do is that you can use this identity, which is basically like picking up the energy of the n and m states, and you can just repeatedly insert this into the commutator. Okay, you pick out this en minus em here you insert k commutators and you pick out this omega to the power 2k here. Okay, and again, like these commutators, the value of these commutators, they can be evaluated using similar operator growth techniques. Okay, there is a way to do it, and it's we were not the one to do it, and these were done by these authors. And what eventually happens is that you can show that this leads to an exponential suppression for high energies, high frequencies. Okay, so just to summarize, okay, so what we wanted was some sort of like analyticity properties and boundedness properties for our Green's function. We have some analyticity like light cone for imaginary frequency and momenta. And then we also have some sort of upper bound on the imaginary part of the Green's function. Okay, there are two bounds, one for small frequency and one for high frequency. So basically, this tells you that this quantity, this integrated spectral density, must fall like must at least at most be like a power law behavior at low frequencies, but it must be exponentially suppressed at high frequencies.
What's epsilon?
Epsilon was here. It again contains the Hamilton, the H. So here, for example, like I have chosen that this H interacts with like not just nearest neighbor, but like it interacts with a ball of radius r. But those are just some numbers. But again, crucially, everything depends on the norm of this Hamiltonian H alpha. So the fact that it has to be local and finite dimensional is pretty important for any of these bounds to work.
That's not the total H, right?
No, this is not the total H. So this is a thing that which I think if we have a bosonic system, this becomes tricky, because the H could be unbounded, like so we don't clearly know how that. There should be something like this, but it's an open question, like how to formulate such a bound for that.
Yeah. Sorry, just the capital lambda, your upper cutoff on the omega frequency.
Yeah.
So this just holds for any capital lambda, right?
Yes, but we did it in with the following thing in mind, that both this lambda and sigma will signify the cutoff. So eventually we are going to do the same thing where we want to use some effective field theory on the left hand side, and so therefore like there will be some natural definition of lambda and sigma, which will be defined by the cutoff of where you can apply your effective field theory, up to what energy scale you can apply your effective field theory.
And, going back to the last slide you showed,
yeah,
can we so this epsilon can also be related to your speed of light, right? Your Lieb-Robinson.
Yeah.
Okay. Maybe I can scribble that later.
Yeah. It will be related, because the Lieb-Robinson thing is like just EAH, and this epsilon will also have the H. So like in some sense, yeah, indeed, can relate. Okay. So now I will come to the more exciting part of the thing, which is how do we apply this? Okay, fine. Like you have some bounds. How do we see it work? Now I don't believe that I believe that I don't need to motivate non-Fermi liquids to this audience at hand. As we all know, non-Fermi liquids are essentially things which are not Fermi liquids. Okay, so for example, like you have characteristic linear in specific heat for Fermi liquids, and for non-Fermi liquids we don't have that. It's the EFT description, as far as I understand, is an open question, whereas for Fermi liquids we have many different ways of formulating effective field theories. Okay, and the crucial thing that that will be central to our applications is that we do have certain phenomenological models which we can use, okay? And that is what we want to do. Okay? So the EFT observable that we actually we will use is the Green's function, fermionic Green's function itself, which at low frequencies and for momenta close to the Fermi surface takes these kind of values, where sigma omega, as Peter had very eloquently, summarized, is something that you can determine from ARPIS measurements. People actually do that. So for us, for this application, this low energy Green's function itself will be the low energy EFT observable. Okay, and what are the phenomenological models that we will use? We will use this marginal Fermi liquid sigma, and then there is this theoretical model, which is that you couple Fermi surface to massless bosons to get this Hertz-Millis theory. We kind of generalize it to alpha between 1 and 2. Okay, and so that's also another sigma that we want to use. Okay, so these are the two phenomenological models that we want to study in this bootstrap manner. And the question then, the first question that I want to ask is that for what values of this lambda, which is the lambda MFL or the lambda Hertz, do these models via Lieb-Robinson causality? Okay, so that's the question we are hoping to answer. Okay, and so in order to do that, the way we want to go about it is that we want to look at the poles of the Green's function at imaginary frequency and momenta. Okay, and we want to make sure that these poles, which are essentially non-analyticities of the Green's function, should not appear in a region where our Lieb-Robinson analyticity says it should be analytic, right? So that's the constraint that we are going to use. This is the part which is okay. So first thing is that, we take the cutoff of our model to be less than h, which is the scale set by the microscopic Hamiltonian. And so therefore, for all practical purposes, what we see in this analyticity plot is just the light cone. Okay, we just see the light cone, and that is what is represented by this. Okay, so the analysis proceeds as follows. We look at the poles of the Green's function at imaginary frequency and imaginary momenta. Okay, it takes this form. Okay, and this is given by this is the form. So the first thing that we want to check is that for small omega, what is happening? Okay, and one can easily see that for small omega, nothing happens. Things like, this sigma omega is basically very slowly growing. So it never, it never reaches a stage where, these poles kind of move up into the the forbidden region. Okay. And so for omega goes to 0, we have the causality is always satisfied. And we assume that the VF star, which is the renormalized Fermi velocity, it depends on the fact that the renormalized Fermi velocity is actually less than the Lieb-Robinson velocity, because Lieb-Robinson is kind of by definition the highest possible velocity that you can have in your system, okay, for information propagation. Okay, so the most dangerous thing that can happen is when omega to approaches the cutoff or where our EFT might start to fail, right? And so the condition for causality is that this lambda must be less than V LR cube lambda, okay? And in order to obtain a constraint on this in this coupling constant, what you do is like you solve for this capital lambda from this equation like this, and you obtain that this coupling constant must be the absolute value of the coupling constant must essentially be less than 1. Okay? And you can try to, this is a pictorial representation of this entire story where, what we have chosen is that we chose capital lambda, the cutoff, to be half of the microscopic scale set by the Hamiltonian, VF star to be 1/3 of the Lieb-Robinson velocity, and we just plotted how the pole moves in this analyticity plane. Okay, so the first, so you can see that for lambda for alpha less than. So I must also say that we see that for alpha less than 1 and for the marginal Fermi liquid, unfortunately, like for all possible frequencies, the velocity is just too small. It never reaches into the non-analyticity the forbidden region. Okay, and you see that this MFL and for alpha equals half, this is just way below the Lieb-Robinson light cone. Sorry, yeah.
Right, but in the when alpha is bigger than 1, aren't I still describing a Fermi liquid? So the self energy is
good. So my definition is that anything with alpha not equal to 2 is a non-Fermi liquid. Alpha was omega square, or alpha was omega to the power alpha. Yeah.
I see.
Yeah. I see. So we still have like between 1 and 2 some models which could be potentially
Okay, but at least in the models that I'm aware of, of these Hertz-Millis type, alpha is less than 1.
So it's kind of, but I can show you some. There are some experimental papers where they try to fit this kind of between 1 and 3 as well. So of course there is no first principle way to get these. These are just phenomenological models, it seems.
I don't know. I mean, maybe I'm misunderstanding. But I would argue that marginal Fermi liquid, so for an exponent omega where alpha is 1, you still have a Fermi liquid. You still have quasi-particles, but barely. It's like the cutoff for alpha where you could still argue this is a particle-like.
Right. So
anything below is called a non-Fermi liquid in condensed matter physics literature.
Yeah, I'm assuming that if the sigma omega that I just described, unless this is like going like omega squared, this is not a conventional Fermi liquid.
No, that's not true. Because if you look at your expression there for your Green's function, stay on the same slide. The first term in the denominator is proportional to omega. Minus your dispersion.
Correct.
That part is your non-interacting quasi-particle. As long as the leading power in sigma is 1 or larger, that non-interacting particle is still a proper fixed point. And so only when the leading order term in sigma has an exponent smaller than 1, that first bit is no longer the leading order. You have no more quasi-particles.
So this analysis, maybe we can talk about this later, but this analysis refers, it doesn't even refer to existence or non-existence of quasi-particles.
But that's the definition of Fermi liquid or not.
I mean, I'm telling you that maybe we can, because probably this is some definition thing, but let me state again what I'm saying, that there are phenomenological models that people seem to study where they are claiming that with alpha between 1 and 2, this is some sort of something which is not a traditional formula. They are trying to model it using that. We are just using that definition that, okay, this is, maybe we can clarify offline. Yeah.
But you say that you don't get any bounds at all in this.
Unfortunately, no. You have to do something more clever for that. Yeah. What we didn't do, what we didn't do is that we didn't use the upper bounds on the imaginary part of the Green's function, or let me restate, we were not perhaps clever enough with how to use the upper bounds, but we believe that these kind of upper bounds that I told you about the spectral density might be able to give you some sort of bounds on these kind of coefficients. Okay.
What about the special case alpha equals 0, what you would have from elastic scatter?
Anything less than alpha equal less than 1 is not, because it's just that the renormalized Fermi velocity is always less than F's. Yeah.
Sorry. So you said you replaced this curve of analyticity with the light cone.
Correct.
So aren't these bounds too strict? Is it the?
Yeah, but if you go into the exponential region, these kind of constraints will just receive some exponentially small corrections. So you can try keeping some amount of this exponential part in your bound, and it just gives you some small corrections. That's it. It makes it weaker, definitely. It's not so strict, but yeah.
You're saying it's a small.
Yeah. Okay. Oops. So the second application that I want to talk about is that of transport. Okay. So now I'm in a different setup where I'm considering, for example, charge transport. Okay. So this is my Green's function, which is the charge density, retarded Green's functions of charge density. So now we have defined it in a way such that this definition smoothly connects to the continuum density operator, because our low energy effective field theory will now be some sort of will be modeled by hydrodynamics, for example. Okay. So then this the IR EFT that we want to work with is just a simple hydrodynamic model of diffusivity with a single current relaxation time tau. Okay, this is also sometimes known in literature as a Maxwell-Cataneo equation. So you have this continuity equation, and then you have this diffusion equation, but with this small modification, which describes how your current relaxes. Okay, I'm not concerned about how it relaxes. It's just that you have certain this time scale tau, which along with the diffusivity and the charge susceptibility will be the EFT parameter of our theory. Okay, so using these two equations, you can solve for this retarded Green's function in this manner, and you get your low energy EFT observable. Okay, how do you then go about this? So what you do is that you input this guy in this upper bound, where you just replace this in this object. Okay, so then basically then it turns out to be a constraint on this d chi, these combinations of d chi and tau, and you just have to be clever enough to play around with it so that you extract meaningful bounds from this. Okay? So the first thing that this is, I'm not saying that this is something some novel result that I'm telling you. It's all it's all known, but what our point is that now you can show this concretely from like some sort of basic assumptions. You provide a minimal set of basic assumptions and you will see this popping out. Okay. The first thing, for example, is that if you choose your cutoff of your theory to be greater than the microscopic Hamiltonian scale, which is set by epsilon, you'll see that this cannot be the case. The Drude model cannot persist to very high energies. Okay, it cannot be a microscopic description. It's pretty natural to expect. But you see here there's a concrete mathematical setup where you see that this is not possible, because the Drude model, like if you look at the high frequency behavior, it is a polynomial decay, whereas our bounds tell us that the Green's function, the imaginary part of the Green's function, must be exponentially suppressed. Okay, so this is something that it immediately tells you. Okay. Then, more interestingly, then comes the part where lambda is less than the Hamiltonian. So we have to choose some scale for our EFT parameters. So we choose that omega and 1 over tau is of course less than the cutoff, and this you remember we had to smear over the momenta as well. And so we choose this to be the mean free path, which is defined in this model in this way. Okay, this is the cutoff of our low energy EFT. Okay, and then I won't go into the details, but I can show you offline. Like this thing is that one of the things that we find is that this of this entire exercise is that this L over A must be greater than some order 1 number. Okay, so what does this imply, and what can you conclude from it? Okay, so this implies that if you assume that the low energy effective field theory is described by some sort of Drude model, it implies an upper bound on the resistivity, which is a proxy for 1 over L, set by A due to locality and boundedness. And it is, I believe this is it's true for conventional metals described by Fermi liquid theory, some version of this Mott-Ioffe-Regel bound. And of course, you will have systems where this is violated. All you can conclude from this is that this must not be, this cannot be described by a simple Drude peak. Okay, this is not something unknown to condensed matter physicists, but this is some. My point here is that you can formulate all these kind of expectations on a concrete mathematical setting. Okay, so anyway, yeah.
Can I ask a question? So here it seems like on the one hand you can say something about Fermi liquid theory versus non-Fermi liquid theory.
Yeah.
And in the previous example, you could not say anything because there was no bound. Here there seems to be one.
Yeah. So here you see one of the things is that I'm working with a retarded Green's function of density, and Green's density, since it's a conserved quantity, it's very easy to identify unambiguously in UV versus IR. Okay, but for the previous case, I was working with the lattice Green's function, like for fermions, which, the left-hand side, for example, if you try to play the same game with this thing, it will also have an incoherent weight. So then it's like sum of 2 objects must be less than something else. So then you can't really have any sort of good constraints on the part that you want.
But here you also put in an additional assumption about the single relaxation rate.
Yeah, that's a
detail. Or?
That's just to make life easier. You can take as complicated EFT model that you want. You have this machinery. Now it's up to you how clever you are with it in isolating different bounds. This thing. Basically that's the game. That you have these strong constraints. You just have to be clever enough to isolate different things. Yeah.
So sorry, on the On this slide still, I don't know how we're doing the time, but I can also keep it until the end. How many more slides do you have?
Just 2 more slides.
So then I'll ask it here. So is the reverse, can we learn something about the reverse put differently? I'm measuring bad metals.
Yeah.
And I see what looks like a simple Drude peak.
I see.
And I'm pretty sure it's not a Fermi liquid.
Uh-huh.
But does this imply that it is a Fermi liquid if I claim it to be a Drude peak, or how should I think about the reverse?
Can I answer this offline? I don't want to say anything wrong.
That's fine.
Yeah. Okay. Maybe I can just also go on. Yeah. So one of the things is that, like, using this kind of this convergence of the imaginary frequency Green's function, imaginary frequency and imaginary momenta, you also get a upper bound on the modulus of the retarded Green's function. Okay, I won't go into the details, but you can work it out. There are some steps, but you get a concrete number in front, basically. Okay, and we have checked that if you apply this to this simple model of diffusion with a single current relaxation rate, it is consistent with the fact that VF must be less than VLR. Okay. All right. Let me conclude. So our applications were pretty basic. So one of the things that one can ask is that, can you do more complicated, can you put bounds on more complicated effective field theories? In particular, for example, in context of hydrodynamics or charge transport in metals, can you account for fluctuations, for example, EFT loops or hydrodynamic loops, for example. Of course, the one I think the most pressing question is that is there any bound on MFL or this zero for Hertz liquid when alpha is between 0 and 1? Okay. Finally, we have not utilized the full power of analyticity and unitarity or boundedness. If we were able to do so, we would have been able to write down dispersion relations and use the full machinery of what bootstrappers use to hammer away at anything that you might be able to throw at us. So one question is can we use formulate dispersion relations with this kind of weird analyticity region that we have in this thing? And finally, one of the things which is interesting is that this upper bounds on the Green's spectral density of the Green's function, this is somewhat unique to the fact that we have bounded lattice systems. Okay, I'm personally intrigued by it because such a upper bound does not exist for continuum models in quantum field theory, for example. Okay, so but there are there are hints of it. For example, in n equals 4 super Yang-Mills at finite temperature, which is basically the dual of one of the possible duals of these holographic models that people have studied. If you look at the spectral density of the temperature-dependent part of the spectral density of the retarded Green's function, you do see this kind of exponential, damping. Okay, and it's not immediately clear how to show that feature in generic finite temperature quantum field theories, for example. So that's also something that I'm thinking about. So with that, I end.
Any more questions? Yes, please.
Anybody else first? Yeah, really interesting. A few questions. So in this bootstrap spirit, have you thought about other constraints you could apply? For instance, say you want to demand that you have quantum oscillations, Lifshitz-Kosovic scaling, something like this.
No, we have not.
Okay.
But it is yes, definitely you can think about it. Like, yeah, I mean, I'm happy to chat. I don't know about it, but like, I'm happy.
So these are things that one conventionally associates with a Fermi liquid.
I see.
So if you demand that those things hold, then also make some.
Possibly. Yes. Indeed.
Okay. One other question.
Yeah.
So you can have a UV description purely in terms of fermions.
Yeah.
But the low energy degrees of freedom don't have to just be fermions.
Correct.
Right.
Yeah.
So maybe interesting thing to consider. So suppose I'm in one dimension.
Yes.
Where actually, there's definitely no.
Yeah, it's like
if I try to apply your machinery to that case, what would I see actually if I did it in one dimension where I have some kind of Luttinger liquid, bosonic
description? Right, interesting. Like, so the Luttinger liquid, if I understand, like at least for the Green's function, it's just some it's some linear dispersion, right? I mean,
of a boson.
Of a boson, yeah. So as far as analyticity constraints are concerned, it doesn't make any difference because, as you see, like, the analyticity constraints doesn't really refer to the fact that whether it was a boson or a fermion. But, the upper boundedness, maybe there is something to be done there. I'm not super sure, but at least for the analyticity constraints, there is nothing because it's just linearly dispersing. It's just a branch cut, right? I mean, it's usually a branch cut in the Green's function, right?
The fermion.
Yeah.
I see. Yeah. So okay, right. You did show us bosonic.
Yeah.
So I'm actually thinking if you can impose like a global symmetry as a constraint, like conformal bootstrap impose the conformal symmetry.
Right.
And now suppose you are within the Fermi liquid phase.
Yeah.
So my definition is the same as yours. And so this is sharply defined Fermi surface. So we suppose have the so-called LU1 symmetry or something like that. And that's a large group. So
Yes, indeed. I don't immediately have a clever answer to that. But I can.
Okay. Yeah. That would be very interesting.
Yeah.
Thank you.
So these upper bounds, those for any retarded Green's function of any operator. Just I think one of your last slides.
To have some amount of teeth in this bound, you want it to be some sort of conserved operator, because otherwise what happens here is that you would have a lot of incoherent weight as well, because you cannot identify the O with the O of the EFT, basically, which you can do very easily for conserved operators, that J here will be J here, and so this thing.
Do you think using methods like this, you could get this causality bound on the diffusion constant? Roughly, it should be D is less than B, Lie Robinson squared.
Yeah, I think yes, indeed. I think roughly this guy is roughly like that, because D you can write it as VF tau or something like that. Yeah. I mean, we can chat after this, but there are ways to rewrite these in terms of
Okay, so let's move the remaining questions to coffee break and take a speaker again.